So intuitively, how does this work? Let's imagine initially our matrix is very weak. And so all the initial sequences get pretty much similar scores, right? We want to use an example. You know, US Congress has 435, the House of Representatives have 435 members. It's represented by, each representative represent their own state, home state, from Massachusetts, California, Texas, and the number of votes or number of seats for each state depending roughly on the population of the state. Okay, so initially you have some, you know, every vote. So now let's imagine if every single day we ask, we have an election, let's take out one seat, wherever the seat is. We ask all the remaining House 434 members to decide where they want the new seat to go. Can you guess what's going to happen? You cast a vote to say, this new vote should come to, I think every state will say, I want this new vote to come to my state, right? So you cast your vote. So basically you have 435 in a hat. And some has Massachusetts, some have Texas, some have California. And then you sample, you pick one. What is it gonna be? What is it more likely to be? Marina? Yeah, more likely to pick a state that's big, like California, like New York City, right? There is a small chance that you will pick Rhode Island, but not very likely. It's a small state, right? So, but then supposedly you pick one, oh, this is California. Maybe the vote that you previously took out was from some, yeah, by chance it could be California too, but now you give it back to California, then California have that vote. Next day, you randomly pick another state or a second seat. That second seat happened to come from Massachusetts. They take it out. And then you ask all the remaining people to again cast their vote in the hat, and you randomly sample out. Oh, this time it's New York. Shoot, Massachusetts lost a vote, and now that vote goes to New York City, or sorry, New York State. And the third day, you do this again. You take out one seat, you ask all the remaining seats to vote, and then you pick one, you sample one, and then that seat will go to the new state. So initially, it's kind of weak, right? However, remember, what are we trying to do in this situation is we're trying to find a pattern that's more or less enriched in your data. In some sense, there should be more hits or more representative for the correct motif, which means naturally California has more votes in there already. New York City has more votes in there already. Therefore, when you do the random sampling, there is a chance that they get selected more often than others. However, once they go in, they will favor their state even more. And so that in the next round, their state get even higher chance of being selected. And then next time you take out another seat, then their state get more and more power in some sense. So once a few sequences come into alignment, they will prefer other sequences that look like them, or they will prefer they all prefer their own state. But if you have a few states, you know, basically, once New York City takes 50% of the vote, it will converge very quickly, because every time you take out a seat, it will go to New York City again, right? So that once some of the correct sequence come into alignment, they will favor the matrix so much that other sequences that look like them will come into alignment quite quickly. And so when is the convergence happening is supposedly the House now is 435 votes all going to New York City. Every time you do, everybody likes New York City, sorry, New York, then that's it. You have no way of going to elsewhere now, right? Because they are so strong. And that's when you have motif convergence. And so let me ask you, so you can see this, the stochasticity or the randomness come from randomly picking a vote. The sampling process creates randomness. if we were to do this House of Representatives multiple times, you know, you start initially with current Congress makeup, and then you say, run this to convergence. Very often, it will converge to big states like California. But if we were to do it again, next time it might converge to New York State. Next time it might converge to, what's another big state? Texas. It will be 1 in a very tiny chance that it will converge to Rhode Island or Connecticut, because they are tiny, they're small, they don't have signal enrichment to start with, right? So you can see, when you try to do this multiple times, you don't always converge on New York. Sometimes in New York, if you run it again, it might converge to California. Even if you initially start the same place, you do it multiple times, it might converge to different places. Okay, so as we mentioned previously, in a hill climbing case, you always just go one step higher. Gibbs sampler kind of, you can imagine if we were to do this landscape way, is, okay. So if you have a landscape, you know, this is the motif occurrence. It's like, if you randomly sample, it might actually jump over to here, or it might jump over to there. It might jump over to there. So because you are randomly sampling, it will give you some chance to jump around. So it's less likely to get stuck in a local maximum. It's more likely, and then, you know, maybe if it's, but then if this peak is so much higher, you know, eventually the correct motif is so enriched, once you are here, it's less likely to jump around. But if you were to start from a few places, I guess with Gibbs sampler, you still start a few places, but you don't need to start with so many different places. It will probably converge to the correct one. Okay, that's how Gibbs sampler work. So we mentioned in motif, you know, how do we know whether the motif is good or not? You actually try to just use the information content. You ask, you know, what is the probability so now you are looking at this matrix, and you're using all these hits, right? So you are saying, okay, the probability of this sequence coming from my motif divided by the probability this sequence is coming from the background. This is for the first sequence, and then we look at the second sequence, and we look at the third sequence, all of them together. You multiply them together. You want to have a big separation. We want this motif or whatever alignment to look a lot like the motif and very, very different from the genome background, right? So yeah, so you do use information content or the relative entropy to decide whether the motif is good. So in this case, if you look at the sequence logo, which pretty much give you the relative entropy, you can see, for example, a motif like this is pretty weak, but a motif like this is pretty strong. You like a good motif like that. But also, yeah, so basically, yeah, you also want the motif to have many hits in your input sequence. If it has more hits, that's also a good thing. They are more likely, yeah, they agree with each other. You know, they agree, which means in this space, you can see 95% of the location basis at this location is a T, very small chance of being something else. And also, you want to see the hits likely to appear in the genome background. For example, sometimes you see a hit that's like AT-ATA, like not so exciting because the genome has a lot of these AT repeats, right? That's not so good. Yeah, so you want to use the information content, but you want this, you want a lot of hits, and the hits look like each other, and the hits are not likely to appear in the genome background. How do we make sure that our algorithm don't get stuck in like these repeat sequences like AT-ATA or some like AT-rich some sequences? Very often we use something called a Markov background, which means when we look at a particular nucleotide, in the background, instead of asking just what is the probability of A in the genome, we ask, if we know the previous 3 bases is CTT, then what is the chance that we're going to see an A? This is called a third order Markov because we're looking at 3 bases before. But then the next base we ask, what is the chance of a T in the genome background? We look at the 3 previous bases. They are TTA. And then if, given TTA already in the genome, what's the chance of seeing a T? And so let's imagine a case where you have 2 sequences in here. And one is TC-AGC, the other is AT-ATA. We know that human genome has some repeat sequences like AT-ATA. There are a lot of such things in the genome. But TC-AGC is not so likely to appear in your motif. Assuming right now our motif is, we are just starting the Gibbs sampler, the motif matrix is completely random, 25% ACGT, so you can see the numerator is the same. But when we try to use a Markov background to score the TC-AGC, you can see here, initially it might be, like this for the T, but then because TC-AGC is not so likely to appear in the genome background, we get slightly smaller numbers in the denominator. Whereas AT-ATA, like by this time, you are already seeing AT-ATA, you are suspecting that you are kind of in a repeat sequence. If you already see ATA, the next one being T is very high. I'm making it up, like 0.42, right? Because it's like a lot of repeats like that in the genome. So the denominator will be higher. And so even if the numerator is the same, if you have a Markov background to correctly capture these type of repeat sequence in the genome, the denominator will be much bigger. And so when you get a likelihood ratio, this will be much more likely to get a better score than this one. And so when you are doing sampling, you will eliminate those really bad repeat sequences, okay? Then you will get the correct motif. So with motif weight matrix update, the advantage is that you can look for motifs for any width. You can look for a motif of 50 mer if you need to. Whereas with word enumeration, you can't enumerate 4 to the 50th. It's too many. It's very flexible with base substitution. You can see here, we can see the motif right away. It's really good to tell you which base is good or bad. The disadvantage is that there is no guarantee that you will converge. Imagine if there's no motif, then you will just keep running. There's always changing, you never converge onto something. There's also no guarantee that you will go to the global optima. You might get stuck in a local optima, right? So you might want to start a number of times. So there was a lot of work involved in there. Since then, there are also more experimental approaches that really try to get the transcription factor motifs. One is called the protein binding microarray, and Martha Bullock's lab at Harvard Medical School is really the expert on this. So they develop these arrays. This has all sorts of different, they use 60 nucleotide DNA sequence in here, which pretty much capture all the possible sequences, like all the possible 10 mers, all the possible 13 mers or something. In this microarray, of course, has many, many probes. And then, and then if you have a particular transcription factor, if you're interested in a transcription factor, you want to know where it binds, you have to tag the transcription factor with some fluorescent. You make a purified protein, you tag a fluorescent, and you flash the transcription factors onto this microarray, and each transcription factor will look for its binding site. So this is the same transcription factor at a time. So for example, in this 60 mer, you might have one 10 mer that's bound. This particular 60 mer also have the correct 10 mer that this TF will bind. And then you kind of let them hybridize, you wash off the junk, and then you shine light and you see which spot light up. And then finally, you collect those spots that light up. You know that each of them probably contains some 10 mers or 20 mers or 15 mers that has this motif. Then you can look for motifs. That's much, much easier to do, right? And so from this a few hundred transcription factors, we have their motifs pretty well characterized. There's another approach which also takes purified proteins. So, but it now uses high throughput sequencing. So you can imagine here the oligos are put on a microarray. But you can also imagine we create a random pool of oligos. It's completely random. And then if we have to purify the proteins, that we use the protein to, so here you see this shape, the round shape things are the protein. We add the protein, and whatever this protein can bind to, those get enriched. You can pull them down. You can enrich for them, and anything that doesn't bind get washed off. And then you enrich for things that bind. But then you can also amplify this. The next second round enrich again, and you wash off the low binding. And then you do high throughput sequencing. You just sequence out whatever is being enriched in this data. And that will also give you motifs. So the SciLex approach by this time also a few hundred transcription factor motifs. And so in the very early days, JASPAR is when we started. We're like, from just literature, curation, very labor intensive. And then protein binding microarray, there were actually many, many later papers. So there's a database called UniProbe. They have all the protein binding microarray motifs. And also there's SciLex motif. Later on, people are doing ChIP-seq. We're going to talk about ChIP-seq in the next lecture. And also a motif, now a database called HOCO-MOCO, which has literature, PBM, SciLex, and ChIP-seq motifs, all a pretty complete collection now. And so nowadays, if you start from some sequence for motif finding, a lot of these algorithms use a combination of de novo motif finding. And if you already have no motif, you just look at whether there's motif, there's a hit or not hit, right? It's easier now. So that's that. Stopping here.